Petra, you're with me, right?
Yes, I'm here.
Okay. So, so Hadoop itself was developed because it represented the most practical way to allow companies to manage huge amounts of data. Um, yeah, so the idea around Hadoop was, see, we are generating a lot of data now from the days of dot-com boom, in the days of Yahoo, and in the times when Google started, the kind of data they were handling is not the kind of data that is built, that Oracle database is built for. So when you look at Oracle database, it's structured into rows and into columns. So that is it's easy to store those type of data in an Excel sheet. It's easy to store that kind of data in an Excel sheet, or what is it called, or Oracle database, or a database application. But we now start generating other kind of data like pictures, like email messages, like videos, like text, comment, tweets, you know, post on Instagram. We started generating all those type of data, plus even stuff like adverts, you know. When we started generating all of that, they are not structured kind of data, and there are a lot of this data. They are voluminous, they are huge. So Hadoop is one practical way that we tried that was developed in order to be able to solve this problem. But Hadoop, as we said before, comprises of three key components. One of them is the map reduce. Map reduce is not, it's just an algorithm. It's just like a simple algorithm. And we are going to go into what map reduce does. Then there is HDFS. HDFS is like the file system. It's like the location on Hadoop where the file itself is stored. MapReduce and HDFS, they provide the basic structure that is needed to support the core of big data function. While MapReduce, the function is to break data into different break a job into different components. HDFS is exactly where the job or where the data is stored. Then the third component is called YAN. And that YAN is just a piece of software, and it helps to coordinate. It's just like a coordinator. It's like a coordinator within the Hadoop ecosystem. Hadoop 2, as it's sitting here, it's an effective framework that, with the introduction of a software layer that is called YAN, that is built on the cluster resource that manages eliminate Hadoop complete dependency on MapReduce. Okay, so I'll get into that. That is okay. So I've explained all of this. So here they said that the component of Hadoop is Hadoop is often compared is called they call it Hadoop ecosystem. And when you look at the living things, how it's trying to mimic how living things interact. And that's why I gave that example of a wedding. If you go to a wedding, at the car park, you will have security men that tell you this is where to park. At the entrance, there are bouncers that are checking if you have an invitation card. Then in there, you have ushers that are telling you where to sit. Then you have people that are serving food. You have people that are serving drink. You have people that are clearing the table. And then you also have like an MC that is coordinating the whole event. It is exactly the same implementation that they have in Hadoop. And that's why it is called the Hadoop ecosystem. It's similar to how living things interact. Before, in version 1 of Hadoop ecosystem, in version 1, it was only HDFS and MapReduce. So for anything that HDFS will need to do, or anything that Hadoop will need to do, it's entirely dependent on the MapReduce component for most of the things that I want to do. But they now went ahead to now build like a component that manages or every other aspect of the Hadoop ecosystem, which is called the YAN. You know. So again, it's an ecosystem. It's an ecosystem because it's a collection of multiple things all together. So so this picture is just a list of the components of the Hadoop ecosystem: HDFS, MapReduce, Yarn, HBase, Hive, Pig, Scoop, Zookeeper, Flume, and Uzi, you know. So all of them are different. Those are the different components of the Hadoop ecosystem. I just want to take time to recognize some people that have joined the class. Kola, I don't know when Kola joined the class, but Kola, you're welcome. Then also we have Chude in the class. Chude is Today is a friend of the house, but it's also joining the class. So today is very technical. It's very technical, especially when it comes to database applications. It's one of our clients currently. So although he's joining the class maybe about 30 minutes late, but I think he's joining the class at a very good time. He has missed some parts, but notwithstanding. I know that Kola probably has a lot of things that he's doing. That's why he has not joined the class. So I want to welcome you guys. There are more people in this class than this. Ayola gave some apologize that she will not be able to attend today. And then talk about Temilade too. Temilade also did not join the class today. Perhaps maybe by tomorrow she'll be able to join the class. I think she's a bit indisposed. Then I think there's some more person. Temitope too. It's supposed to be in the class, but I want to welcome you guys. Today, welcome. Kola, you're welcome.
Thank you, sir.
Okay, so yeah, so before you guys came, we're talking about the Hadoop ecosystem. Okay, so we're talking about the Hadoop ecosystem. I'll quickly just run through it because I think this is very fundamental to this class. So just for the benefit of people that just joined, so Hadoop ecosystem was originally developed by Yahoo, and when you look at the kind of data that Yahoo manage, it's largely unstructured kind of data, you know. So it was not like the relational kind of database, it's not relational kind of data that Excel can take or Microsoft SQL Server or that Oracle can take. They are largely unstructured data from emails and from even adverts that they were managing and from news and or a lot of different kind of things and pictures and videos, all of that together. So they were the original inventor of the Hadoop 1 version. But after a while, I think they released it to the market and then made it open source. And they handed it over to Apache, which made it to have an open source license. So everybody can have access to the kernel, to the code, and stuff like that. We said that there are three key components of the Hadoop ecosystem. One of them is the HDFS. HDFS is called the Hadoop file system. We have the MapReduce. MapReduce is like an algorithm that takes a big job and splits it into smaller components, or takes big data and break that big data into smaller components. And there's a third component that is called the Yarn. So Yarn is just like a piece of software that helps to coordinate, that makes the Hadoop ecosystem a lot more effective. You know, you need a coordinator, you know, that manages all of this. Then so then we also talk about Hadoop itself. It's an ecosystem. It's not just like a software, you know. It's not just like an ordinary software. Hadoop is an ecosystem that comprises of a whole lot of things. Before you guys came in, the easiest way, one way that you can like reflect on what Hadoop is by looking at the ecosystem, like living things ecosystem. we in biology that we did those times, there is ecosystem and there are different people in the ecosystem. There is plants in the ecosystem, there is sun in the ecosystem. So, and there's also human beings in the ecosystem, there are animals in the ecosystem. The sun gives food to the plant then becomes food for the animal in the ecosystem. After the animal eats the plant, after a while the animal will die and goes into the soil in the ecosystem. After it goes into the soil, it becomes manure for the plant, and then with sunlight again plus water in the ecosystem. That is one way you can think about Hadoop. That is exactly what they tried to mimic when they were designing Hadoop. Another way you can look at Hadoop is you imagine a wedding event, and you drive to that wedding event. There could be security guys at the car park that are telling you this is where to park your car. Park your car in this particular space. Then after you park your car and then you move towards the hall, there are bouncers that are checking your IV. When they check your IV, they will know whether you're invited to the party or not. Then after they grant you access into the hall, then there are ushers that are telling you this is where you should sit and this is where you should not sit. This place is for the groom and this place is for the bride. After you've gone past that again, then you are seated, then there are people who serve you food, and there are a different set of people who serve you water, and there's an MC that is coordinating the whole event. Hadoop is an ecosystem, and that's exactly how Hadoop is meant to function. Now, there are different components of Hadoop. The same way in an ecosystem, there are different components. So the same way in Hadoop, there are different components of Hadoop. So you have the HDFS file system, which we are going to talk about. You have the MapReduce component, you have the YARN, you have the HBase, you have Hive, you have Pig, you have Scoop, you have the Zookeeper. I know there are a lot of technical guys in the room that can relate to some of these things I'm saying. So look at the Microsoft SQL Server. If you look at Microsoft SQL Server, the way they have built it's a little bit like some kind of an ecosystem where you have a database component that holds the data. Then you now have a data migration tool. So anytime you want to migrate data from one location to another, that component of SQL Server that is called SSIS does the migration. There's another component, Microsoft SQL Server Analytical Service for when you're doing analytical operation and so on and so forth. The same way in Hadoop, the HDFS is like the file system. The MapReduce is that component that splits the job into smaller chunks and then distributes it across different resources. YARN is like a coordinator of that ecosystem. HBase and Hive. HBase is like a database for unstructured data. Hive is something that is close to a database for your structured data. Scoop is like your Microsoft SSIS or your Oracle data integrator that you use to move data all around. Zookeeper, it's also like a coordinator, then Flume and the rest, which we are going to go into them. So what you need to do is just to understand what exactly does this component do. And it's simple. If you understand what the component does, then it makes your life a lot easier. So we'll be going into the details of all of these different components of the Hadoop ecosystem. So this is how they are all connected. Hadoop itself is an open source, but there are some commercial distribution of them out there in the market. On AWS, there's EMR, which is in the cloud, which is in the cloud. There is the Apache distribution, there is Cloudera distribution, there is Hortonworks distribution, Intel has its own distribution, there is MapR distribution. These are different companies that have taken the Hadoop ecosystem, they have added some extra components on top of it, and then they put it out there for people who want to make use of them. Those people only pay them for support, while the license is open source license. But if Cloudera is going to be supporting you, then you need to pay for that support. Then there are several different components of Hadoop ecosystem itself. BP, Hive, HBase, etc. All of them are all there. And even as we speak, there are other people that are even building other components on top of the Hadoop ecosystem. But the core of Hadoop ecosystem still remains your HDFS, your MapReduce, and your YARN. Please, any question at this point before I move forward? Okay. No question.
Though I came in late, but I hope I can.
That is true that I speaking.
Yes, sir.
I did now.
Fine, sir.
Well done, sir.
Well done, sir.
Okay, so let's continue. Please, if you have any question, feel free to ask me. There are going to be makeup classes. I can assure you of that. They are definitely going to be makeup classes.
Okay, fantastic.
For classes that you have missed. Okay, so let's talk about HDFS. So HDFS it's like HDFS is like a data service that offers capabilities for you for Hadoop to manage high volume data and high velocity data. It's a data service, and another way I can put that is it's like the storage. It's like the location exactly. It's exact location within the HDFS framework is the location where the data itself is stored. And unlike the traditional file system that constantly read and write, HDFS only reads once. It only writes once, but it reads many times thereafter. And I will give you a classical example of that. If you look at, for those that, yes, I think a lot of people, maybe except only Mary, that cannot relate to this. If you look at the transaction table on Finacle, for instance, transaction table, you only write once on transaction table. You cannot go and edit what you have written on transaction table on Finacle. So you only write once, but you read as many times thereafter. You cannot edit what you have written there. You understand? So even if we discover that what we post on transaction table on Finacle, there is a wrong post, what you go and do is that you go and enter another entry. It's not like you go and delete the wrong post that you have made on transaction table, So that is how Hadoop exactly is designed. It's designed to write once, so you write once to that location. Once you write once, then subsequently you just need to read what you write there. But they are now going to be like indexes. They are going to be indexes that you call that will tell you anytime you want to read that data that is written in a particular location. It's just quickly going to point to this is where you find it. If what you want to read is about maybe internet banking transaction or POS transaction, it is stored in such a way that you can easily reference it without necessarily start scanning through the whole data set, and your data is going to be extremely very slow. That is how that is the underlying concept behind the design of that Hadoop ecosystem. The file system itself is distributed. Remember, in the previous class, we talked about distributed computing. We talked about parallel computing. So you think about distributed file system. when it is not distributed file system, so if you have like maybe 2 gigabytes of data, the whole 2 gigabytes of data is stored inside one single location. So if you look at your Excel, for instance, if you are going to store data on that Excel, everything goes into one Excel sheet, you know, everything goes into one Excel sheet. But if it is distributed on Excel, you can have it in such a way that everything that is A goes on a particular file. Everything that is B goes on a particular file. So you imagine a very big Excel file that contains, say, 200 million records of Nigerians. Imagine you now want to open that Excel file on your computer. It's going to be very slow. In fact, it will take a very long time to load the whole of that Excel file into memory and then to be able to open it. And if you want to scan something from that Excel file, then it will be very slow. Now, we can now think of, okay, can we distribute this data on this Excel file? Instead of having the whole 200 million Nigerians stored on one single Excel sheet, we will have people that their names start from A in a different Excel sheet, people that their names start from B on a different Excel sheet, C on a different Excel sheet, D on a different Excel sheet. So anytime we are looking for Blessing, for instance, Blessing Oladeji, we just need to know that we're going to search for him on the Excel sheet that starts with B. So we will not need to load all the data sets into memory. That is distributed file system, you know. So the data, everything is not stored into one single location. It is distributed across multiple disks, you know. It is distributed across multiple disks and across multiple computers. Note that it's distributed across multiple disks, distributed across multiple computers. And then there's now going to be something that holds the address of where each of those components, where they are stored. So all of those data sets have been distributed. Something we need to tell us anytime we are looking for maybe people that are stored with A will tell us, okay, you find it on this computer and on this disk on this computer, and so on and so forth. You know, please ask me any question if you have any question at this point. Okay, so
I didn't get, there was a point where you talked about writing only one transaction on like a daily transaction table.
yes.
I was lost for a while. So maybe, sorry, if you can take that again. There's only one record you can add per.
Okay. Okay, so the way Hadoop is designed, Hadoop is designed, no, HDFS, not Hadoop, not Hadoop. Yeah, so we are talking about HDFS now. HDFS is designed to write once. You write once to the file, but subsequently.
So like an Excel now, I can. So it's just like an Excel now. For every cell, I can only write one.
Yes.
Another
you
one.
can only write one to that Excel. If you are going to update your data, if you are going to be updating that data, you create another entry again. Okay, and you now need to have a pointer that is saying that there is now a new version of that original data.
Okay, so much like so for a data I already have, can I add like a duplicate data or a unique constraint to come out?
So what it means is that you need to, in that, okay, so let me give you an example. So this is the example that I gave. Look at your transaction table on Finaco. Transaction table on Finaco. Transaction table on Finaco does not get updated. So for instance, so if say I wanted to post 5,000 naira to a customer, and I now mistakenly post 50,000 to that customer.
Yeah.
That entry of 50,000 that I posted, I cannot go and write an update statement and say, okay, change this, you change this 50,000. It's not like it's not possible. You can do that update.
Yeah. But instead, you would add another reverse and add a new record of 5,000.
Exactly. You now need to add a new record of 5,000 and add another record of minus 50,000.
50,000. Yeah.
Exactly. So that is exactly how Hadoop is also designed. So it is designed in such a way that you write once, but you now read subsequently thereafter. That is what's HDFS. Sorry, HDFS, not Hadoop. That is how HDFS is designed. So there are some kind of data, you just need to write them on. So look at Twitter, look at all those stuff that are on Twitter. You know, all those things that are posted on Twitter, they are written ones. When you post pictures on Twitter, all of those things, your email, they are written ones, you know, they are written ones. So subsequently, you can go and be referencing those things that have been written. It's not like you go there and update, you know, and update it. If you want to, if I send you an email, that email, it's a big data, it's unstructured data, it's written once. So if that email, where it is stored, where the email is stored in the cloud or in the platform where it is stored, it is written once. So even if you are recalling that email, it does not go there to delete it. You just probably set a flag that it's no longer available. You just change the flag. Or if you are recalling it, it creates a different entry entirely. But that one that you have created is always there. That is how that HDFS is designed. Does that make sense? Am I able?
Yes, it makes sense. Sorry, I was talking. I didn't know the mic was muted. Yes.
Okay, thank you. So let's look at some of the components of the HDFS architecture itself. Let's look at some of the components of the HDFS architecture. So now, this is interesting. This is not too technical. It is not too technical. So HDFS architecture. So HDFS has its own component, the things that it's made up of. So one of those things that HDFS is made up of is called name node, and the other one is called the data node. And the way it works is that HDFS works in form of a master-slave. It works in a master-slave architecture. And why it has to be so is that data is duplicated, you know. Data is duplicated across distributed file systems. Data is spread across distributed file systems. So there should be somebody that is going to like take the lead, you know, that is going to coordinate, okay, you this data, go to this point, you this data, go to the other point. So HDFS works in a master-slave environment, and you have what is called a name node. So, and you have what is called data node. The name node is the name node is like the master, you know. The name node is like the master, while the data nodes are like the they are like the slave. They are like the slave that is it, though is the data node that holds the data, but the name node is like a dictionary or an in what is that thing? What is that thing? Sorry, hold on. It's like a dictionary. Hold on. There is this thing at the back of a Bible, concordance, exactly. Concordance at the back of a Bible, where say if you are looking for, you don't know where you find the book of Ecclesiastes, for instance. You go there, it will show you that you find it in page 13. You now go back and start navigating through page 13. So name node holds information about all the data. So it's like a dictionary for metadata. While the data node is the exact location where the data is stored. So data is stored somewhere, but the name node is what holds information about where the data is stored. What some of you that know, what some of us call index, but this is a lot more than the index that we know. So when you don't index a table, for instance, when you create a table, if that table is not indexed, you see that table it will be very slow, because anytime you want to run a query against that table, it's going to scan through all the data set before you can find it. But when a table is indexed, what the index holds is that index holds information about everything that is on the table. So it starts the address of where you can find everything on the table. So when you run a query against a table that is indexed, it runs a lot faster because the index will help you to point to, okay, this thing that you're looking for blessing, go to file number 13. On file number 13, that is where you find blessing. It's just as simple as that. So when we say it runs a master-slave architecture, the way it is that the name node is the master, and what it does is that it holds information about all the data sets, while the data node is the exact location, is the block, the exact location where the data is stored. Please, any questions before I move forward? If it's too technical, please let me know that it's too technical, but I think it is very, very simple. It's very simple. Somebody gave me a feedback last week for the class last week Saturday. The person said to me that, blessing, you scored 69%. So the person also gave me an idea that I should look for a whiteboard marker. That I should look for a whiteboard marker, or I should look for a computer where I can write in order to demonstrate some of those things I'm trying to talk about. But this is very simple. I'm going to explain it one more time, but it's very, very simple. So you have data, and we said that it is distributed file system. So if it's distributed file system, it means that there could be 20 computers. And those 20 computers, they are storing information about different data sets, But all of them, they are organized together in form of a cluster, So now, if I'm going to be storing something on any of those 20 computers, I need something that would be the reference point, that would be the address to say that this data that I'm storing, this is the exact location where I'm storing the data. So that anytime I want to retrieve that data, anytime I want to query that data again, I can query it very fast because, of course, if HDFS cannot guarantee speed in data retrieval, then the purpose is defeated, So name node is that component that holds the addresses of all the data sets and where they are stored, and name node is just that location. No, data node is that location, exact location where the data is stored. Any question before I move forward? Okay. I'm assuming no question. So for name node, the blocks are stored in so blocks of data. The blocks of data. When we say blocks here, we are talking about the data itself. The data set is stored within what is called data node, and it is the responsibility of the name node to know the block which holds on which the data node completes a file. Okay, so I can explain that in I want to write. Let me see. I want to write. See. Okay, so hopefully by tomorrow's class, I'm going to set up properly. I'm going to switch my computer to a computer where I'll be able to write on the screen. So I think Microsoft team has a whiteboard marker component. Let me see, whiteboard marker component. I'm looking for a white. So I'm going to research it. I'm going to research a way that it will be very easy for me to translate this thing. Without really talking too much. But the way it is very simple. I just need you to open your mind. The real data is stored on data nodes. Data node is stored somewhere. Or the data is stored on the data node, while the name node holds the information about where the data is stored on the data node. I come back to my Excel example. We have the database of 200 million people in Nigeria. So all of these 200 million people, if you decide to store all of the 200 million people in a single Excel file, what it means is that anytime you want to load that file, the file is going to be very, very slow. You know, for you to even search for something on that file, it's going to be very, very slow. You know, so we now decide to say, okay, let's even split everything into different Excel file by the name, by their name. So everybody whose name starts with A, the person will stay in Excel file number 1. If the person's name starts from B, to stay on Excel file number 2, and so on and so forth. So that is the data set. That is the data. Now, we now want to store this data. If we are going to be storing them on a distributed computing system, and we said that in a distributed computing system, there are many computers, independent computers. Each of these computers will have their own disk space, you know. So by the time I want to store all of these, maybe 26 files now, on maybe 10 computers, I need to know for A to C, on which computer am I storing it? I'm storing it on computer number 1. D and E, I'm storing it on computer number 2. But who holds the information about where I'm storing each of these files? You know, it's going to be the name node that holds that information. Now again, remember in Hadoop ecosystem, there are also redundancies. We also create redundancies because if we store data, if we have broken down that data into smaller chunks, 26 different chunks, there is A, there is B, there is C, there is D. What if A crashes? If A crashes, what is going to happen to that data? That means we are going to lose the record of everybody that their name is stored in A. So we also create duplicates. So there are 2 duplicates of everybody whose name starts with A. We are going to store 1 duplicate on computer number 1 and the second duplicate on maybe computer number 10. So even if what we lost is computer number 1, we still have not lost the record for people that are in A. If what we lost is the Excel file for people that are in A on computer number 1 or computer number 10, there is no problem. There is still another file somewhere that holds information on people that have their name starting with A. And it is the name node that will help us to track all of this. So name node is very critical for the correct operation of a cluster, you know. So name node itself is replicated. So that same name node, because it holds the address of everybody, is very, very critical. So anytime we want to access anything, if the name node is not available, we'll not be able to access it. And if that name node too becomes corrupt, it means that we lost information about where everybody is kept or where all the data is kept. So that name node itself is replicated to guard against failure. So name node, as I said, it acts like a traffic cop, like a traffic police that is saying, okay, you go to this place, you go there, what are you looking for? This is where you find it. What do you want to write? Okay, go to that location and write it on that location. You want to write Blessing Oladeji? Okay, go to computer number 15 and computer number 3. Go and write Blessing Oladeji there, because those are the 2 computers that hold information on Blessing Oladeji. You want to read anything on Blessing Oladeji? Once you query it, it tells you, okay, go to this computer, that's where you find it, and all of that. So data nodes, or the name node, constantly interacts with the data node. There's a constant interaction between both of them. And each time anything happens to a name node, if a name node goes down, so if you decide to like shut down one of the computers within the cluster, there should be a communication between that name node and the data node that, okay, this particular data node is no longer available. And if you turn it back on, you should be able to tell it immediately that it is now available. So imagine how Hadoop works. It's something that is complex, but it's very simple. You know, it's very, very simple. And that's why I decided to use the example of a wedding. You go for a wedding, a bouncer tells you where to go, an usher tells you where to sit. The person that brings food knows where to serve you and stuff like that. Exactly the same stuff. You know, please ask me any question if you have any question. Otherwise, we still proceed. So let's talk a bit more about data node. So data node is like the, as I said, data node is the exact location where all of this stuff, where they are stored, you know. So the data node is, it provides what is called heartbeat message to detect its availability. And it provides that heartbeat message to the name node. So the data node needs to consistently communicate with the data node, you know, so that it goes available. And its data node is the exact location where the data is stored on the disk, you know. So heartbeat will mean the communication between main node and data node in case that comes up in your exam. So I'm moving on. Petra, ask me one question. Kola, ask me one question before I continue. I need one question from you guys before I continue. Just to be sure that I'm not the only one that is here.
You're not the only one, no. At some point, I stepped out, to be honest.
It's interesting, Abby.
I am here. You're not the only one.
Okay, thank you. Thanks a lot. Thanks. Okay, so some of the features of HDFS. Remember when we're talking about virtualization, yes, we talk about virtualization. We said, you know, for virtualization, there is partitioning. So you can take a physical infrastructure and partition it into different virtual machines. We talked about encapsulation, you know, encapsulation. So you have a lot of things. You have like a computer given to you, but you are not the only one that has access to that computer, but you have access to everything that is available to that computer to you, but you are not the only one that have access. Other people too are also having their own view of that computer in different virtual environment. So the same way HDFS too has some of its features, you know, because how do you know that this data has not gone corrupt? How do you know that that everything is still working fine? You know, so some of those features that it has is, number one, it keeps a transaction log. You know, it keeps that transaction log and it tracks that transaction log every now and then. So if I write something to a particular name node, that log is kept. If that thing is updated in such a way there's another entry, it is logged. You know, if there is a delete command, that this data should no longer be available to user, it is logged. You know, if a node went down at a particular point, it is logged. So one of the features of HDFS is that it keeps a transaction log. Number two is that there's a checksum validation. So there should be a way that we should be able to validate data. So if there's a big data set, you know, there's big data. But remember that big data, for data to be complete, if we decide to break it down into smaller components and distribute it across many disks, if you want to combine it together into one, there should be something that will help us to know that, see, we are combining the right things together, you know, or that validation or that verification is done through what is called checksum validation. It's some kind of an algorithm. So So each time I split the data, so there is huge data that is coming, I need to split different disks. I'll need to assign, like, there's an algorithm that will help me to break it down, and then I'll now assign like a checksum validator on a component of that file. And anytime I now combine it together, by the time I combine it together, again, I need to go and validate, okay, is it coming with the right checksum? Then also for HDFS, there are data blocks, you know. There are data blocks that are duplicated, you know, so which ensures that if one server is not even available, the data node is still available. One easy way I can explain this. Look at this diagram. Look at this diagram. So within this data node, so this is a name node. This is a data node, and within this data node there are different disks. There are different disks in this. So when there is no heartbeat, means there is no communication between the name nodes. Yeah, when there is no heartbeat, it means that there is no communication between the name node and the data node. Now,
sorry, as a layman now, can you explain this diagram to me?
yes, I'm trying to. That's what I'm trying to do. But okay? So hold on. Let me just finish what I'm trying to say.
Okay, sorry.
Then I'll now explain the diagram. So I'm taking a deep breath. Yeah, you know when you have technical guys in the room, you just need to be very sure so that they'll be able to relate it to what they've always known. So now, I'm trying to say, so there are different disks. So each data node has multiple disks. So if there's a snapshot of data that I'm bringing into a data node, it is not just stored on a single disk, it's also replicated across multiple disks. So there could be replication across multiple disks within the same data node. There could be replication across multiple data nodes. So this is a data node, but this is another data node. There could be replication across multiple data nodes within the same cluster. Why all of that has to be done is that, see, we just need to make sure that we avoid a single point of failure. We don't want a situation where if a node goes down, or if a data node goes down, or if a server goes down, then we are done for. That means we no longer have access to the data. So that explains that part. Now, to answer the question that Trudy asked, Blessing, can you break this architecture down and simplify it for me? So look at this. First of all, there's a cluster. A cluster is a collection of multiple servers. So how can I create a cluster? So I take my computer with your own computer, Trudy, with Petra's computer, with Mary's computer, and with Cola's computer. I take all of those computers and I connect them together within the same network, using some software. I can create a cluster out of that, So I can create a cluster out of that. So for each of those clusters, there is a computer, there is a data node. There will be at least a data node in each of these clusters. So when we say a data node, that data node can translate to a disk. So there's a disk on your computer, there's a disk on that person's computer. Both of them have been connected together into what we call a cluster. So let's say that cluster is called HDFS cluster, number one. But that cluster is made up of, in this diagram, there are three servers. Server number one, server number two, and server number three. So there are three servers. Now, server number one has only one name data node. Server number two has only one data node, while server number three has two data nodes in it. Now, but there's a name node. Remember, we said that the name node is like a dictionary. It's like index or like a concordance that holds information about all the data that is stored on all of these disks. So maybe everybody from A to F is stored on this data node in this server. This name node has that information that anytime I'm looking for anybody that the name starts from A to F, I should just go to this data node. That is where I will find it. Then if the next one is F, G, from G to T, this is where you find it. The name node has that information and the data is stored here. And then if the last one, T, U to Z, this has that information is stored in this particular name node. That is one. So there are multiple. There is one cluster, but there are multiple servers, and the data is replicated across these multiple servers. You understand? And because the data itself is stored on the disk within the data node, so there must always be communication between the data node and the name node, so that if a data node is no longer available, so in this case, this particular data node It's not available. That is why it's painted red. So there's no heartbeat between it. So there's no communication between this data node and it. So the name node will know that this disk is not available. So anytime I'm looking for data on this disk, I just know that this disk is not available. I cannot find the data on this disk, except if there's a replica of the data on this disk on another disk. I'll know that, okay, don't look for it on this disk because this disk is not available. Go and look for it in this other disk because this other disk has the replica. That explains the diagram. Does that make sense? You are muted. Hello?
Hello?
Yeah.
We can hear you.
I'm waiting for feedback, really.
Okay, so I got confused at the point. I got the definition of your clusters when you were talking about the data nodes as computers. Then when you now talked about server 1, server 2, I think I got lost at that point.
Okay. So, okay, so let's start with, so what you got, that is correct. Server 1, server 2 is just additional information. So when we talk about a cluster is made up of a number of computers. So let's call those computers, let's call them servers. Let's call those computers servers. So you understand? Let's call those computers servers. So
Okay.
here is a server, independent computer. This is another server, another independent computer. Here's another server, another independent computer. But we have installed Hadoop on them. We installed Hadoop on them, and we have now set them up in form of a cluster in such a way that each time data comes, that data is distributed. Remember, distributed file system, distributed computing. That data is distributed across these 3 servers, So when that distribution is done, there should be somebody that holds information about where exactly the data was distributed to. Was it distributed to this particular computer in this cluster, or it was distributed to this particular computer in this cluster, or it was distributed to this particular computer in this cluster? It is the name node that holds that information. Does that make sense?
Yeah, I'm clear. It's just the server thing and I'm clear about it.
Okay, thank you. So I think I've explained the server thing now, Abi. Please now tell me if it's not clear. I'm ready. I'm here for you.
No, I'm clear with it now. I'm clear on. Yeah, maybe I'm muted when I was talking.
Okay, so I can explain it again, or even privately if you want me. You can call me anytime. Okay, blessing, please explain this thing to me. Maybe I got it confused at some point. So that explains that part. Then the third thing about so the data block. So these are the data block. All this stuff. This stuff in the name in the data node is they are like the data blocks, or even a disk can be partitioned further into smaller units. So each unit can now serve as a data block. So it is in that data block, the data itself is stored. So there is a lot of hierarchy. There's a lot of hierarchy that exists within the HDFS architecture. There are the blocks, a number of blocks to form the disk, a number of disks to form the data node. So, and all of this information, they are transparent to the name node. So, exact location on the data block where the data is stored, the name node, exact disk where it is stored, the name node, the disk. So it is something that is simple, but a complex combination of multiple hierarchies. Then there is pipelining. So HDFS also supports movement of data from all of these different components. So it supports the data movement across all the different components. So the data block, it's like the primary component of that HDFS file system. You know, a block server refers to a server that stores data in the file system. So a block is like that is the exact location where the data is stored. You know, there's periodic validation. The address, the information about this data block is stored in the name node. It's always available in the name node. In many cases, it's replicated. There's replication. There is pipelining, which means that data can flow from one name node to another name node. So a name node, a data node can get feed up. If a data node gets feed up or a block gets feed up, then it may need to flow into another data node. So that process is called like pipelining. You know, data node support direct access. So a data node can support direct access for different client applications. So if an application wants to access data on that data block, it supports it, and the information is always stored in the name nodes to guarantee its availability. Then we talk about the checksum validation, and why that checksum validation is important is that in multiple data blocks can hold maybe one information. Multiple data blocks can hold one information, especially when the data is very large. And remember, we did a training for Shell, so they now give us access to some of the data that we use for that training. Seismic data from that they generate from their oil and gas kind of business. I can tell you one single file from the location they gave us, one single file was about 300 gigabytes. One single file was 300 gigabytes. So you imagine if I put like 3 of those files on my computer is 1 terabyte. So if I put 3 files on my computer, this my computer is completely filled to the brim if I just bring 3 of those files to my computer. So in some cases too, when the data is very big, so the data can spill across multiple data blocks. So it's the checksum validation that I used to know that okay, it's the same data that we are combining together. Yeah. So that is that on data block. Then
Sir, I have a question.
Please ask me.
Okay, I'm not clear with data block and what's this other guy? And data, is it data server or block server? What do you call them?
Okay, so it's simple. You want to talk about data nodes. There is data nodes, there is data block, there is disk. So all of it, they are just different hierarchies. They are in hierarchy. So look at this now. The number of disks are combined together to make data node. So in this disk, inside this disk, there are different blocks. Okay, so I'll use my what's it called? Let me use my wedding party example. So in that wedding party example, you scale through the bouncers by the entrance, have an ID, and they ask you, okay, go and sit down on that particular chair. That chair is like a data block. That is the exact location where you are seated. So imagine maybe somebody, anytime when you came in, somebody is now writing, push him or came in, and push him or sat down on this particular chair. That chair is the data block. But remember, on the chair where you are sitting there, there is a table, and that table is for maybe 20 people. So the table has a table number. So maybe you are sitting on table number 15 and chair number 1 on table number 15. So the chair is the block. The table is the disk. The table is the disk. Then there is a name node. There's a name node. So they can say that, okay, because you are coming for the groom's family, this particular side is the side where groom's family sits. You understand? So it is just different partitions. It's just different partitions or different hierarchies that exist within the Hadoop architecture. Now the data block is the smallest component. That is like the seat where you are sitting down. That seat has an address, but also you are sitting around the table. That table too has an address. You are sitting on table number 15, seat number 1. Seat number 1 on the groom side. And somebody is noting all of that. The guy that is noting all of that, that guy is called the name node. So if somebody just came that, you are looking for a guy, his name is Kushimo, they say, okay, go to the groom side, table number 15, chair number 1. That is where you will find it. That information is stored on the name node. So data block is just the minutest hierarchy. Does that make sense?
Yeah, it does. Thank you.
Thank you.
Yes, it does.
Thank you. So moving on. So also the way HDFS manages it is that there is a replica for every data block. So for every data block, there is a replica for it. So and why we said that? We said that before, so that there will not be failure. So for every data block, for every data block, so if Kushimo is sitting on a chair, for instance, within that event, there's another Kushimo that is another way, somewhere again. You understand? Then you are physical, but data, you can have replica of data. So at least that keeps at least one replica of that data block. So anything that is on this particular data block is replicated on another data block somewhere else, in such a way that if the disk goes down or if that data block is corrupted or anything happens to it, at least the data will not be lost, and it places the second replica on a different rack to guard against a complete rack failure. So let's go back to this. So if Kushimo, for instance, is on this particular block here, is on this particular block, there is going to be another Kushimo that is on this other block here. So in such a way that if it is the whole of this server that went down, there is no shaking. We've not lost data on Kushimo because there's another replica of it that is somewhere here. So because you can see this server is different from this server. So if this server goes down, if this particular server goes down, the data is still available. It's still very much available. So that is how the block is. Then, in fact, in that case, there is a third replica again that is kept. So there are multiple replicas depending on how much money you have. Depending on how many node clusters you have created. So depending on how many node clusters you have created, there are many replicas that are created. So all of those replicas guarantee the data availability, and it sends additional replicas to a random location in a local or a remote server. So there are just many replicas that are created in such a way that you imagine that how can Amazon, how can it be able to support the whole world at the same time? And there is no failure. Every time, in some companies that may have worked before, every time we are always doing maybe disk upgrade, or maybe there is a data corruption or something, we are trying to do migration and the rest. How is Amazon, the AWS, how is it able to do all of that for all of the systems across the whole world? Of course, they have replicas that they have created. So many replicas in such a way that your data is always going to be available, And of course, the day Amazon comes and says that they are down, that is the day they are out of business. The day that there is one single incident of data is no longer available, some people stop their data is no longer available, then that is the day that they are completely out of business, I'm taking a deep breath before I continue. So, in continuation of that, go on.
Listen. So does this certification, does it covers for Amazon certification also?
Amazon Web Services.
So AWS Web Services certification. No. It does not cover for it, of course. So for that certification, it's simply for you to know how to manage the platform, the AWS infrastructures and AWS platform. So this does not extend into that. Or of course, the other time I said that there are different flavors of Hadoop. I said there are different flavors. There is AWS Amazon one, there is Apache one that is open source, there is Cloudera, there is Hortonworks, there is Intel and the rest. So even Hortonworks, they have their own certification if you are going to be managing Hadoop within their own environment or for the one that they have developed. So the same way for Amazon is completely different. But with the one that is being taught in this class is the open source one that is publicly available to everyone. So if you now want to gain specialty in the one for AWS, of course, you need to also access that body of knowledge somewhere. So moving on, I think you are nodding your head in saying yes. Okay. So moving on. So HDFS Federation, there's what is called HDFS Federation, which makes it possible for that cluster to scale by adding name nodes or by even adding additional data nodes, each of which can manage a section of the file system. So of course, when you look at this cluster, for a business that started very small, they can start with maybe a three server cluster. But as the business begins to grow bigger, they will keep adding other nodes. They keep adding other nodes to the cluster. They keep adding other nodes to the cluster. So it's HDFS Federation that makes it easy for you to be able to scale and expand beyond the original architecture that you started with. And the way it works is that you can easily add additional nodes to it. You can easily add additional data node or name nodes in order to avoid a single point of failure. So that is going to help you to guarantee high availability. It is, if you hear that a Hadoop cluster went down, the guy that implemented it should be sacked because the availability or avoiding that single point of failure is part of everything that they have thought about in that design. So if it went down, it is likely not coming from the software itself. It's maybe coming from how the implementer implemented it. Okay, so that is that on HDFS. Let's move to MapReduce and see how MapReduce. Let's see how it works. So I'm taking a deep breath, and I'm going to continue. So it's not easy to really to bring all of these things together in a way that makes sense. Okay, so we said there are three core components of Hadoop. One is the HDFS, and we just finished talking about HDFS. It's like the file system that is made up of different hierarchies. The core component of the HDFS is the name node and the data node. But for the data node comprises of disk, and below the disk you also have the data blocks. All of them, they are organized in a way that guarantees high availability and like prevents single point of failure. Now, the other component is called MapReduce, and what MapReduce does is that MapReduce is it's an algorithm. It's an algorithm, and what that algorithm does is that you just split a job into smaller jobs, or it splits data into smaller chunks so that it can be distributed across the disk. So if we say it's big data, it's a lot of data. We are using the example of 200 million Nigerians. So it's a whole lot of data. Assuming that data is coming in Excel, for instance, and you want to load it in Hadoop. So we might need to find a way to split that data into smaller components, and then distribute it across multiple disks, and then duplicate it or replicate it in a way that we can guarantee that even if any disk goes down or any of the server in the cluster goes down, it's not going to be failure. For people that are not very conversant with that word server, please, I want to beg you. Server, computer, they are like the same thing. Server, when I say server, when I say computer, I'm actually interchanging the same word for themselves. So what MapReduce does is that it takes a job and then splits that job into smaller components. After splitting it into smaller components, it now distributes it to different resources that are available. Then the execution or the operation is performed on that job. After the operation is performed on that job, MapReduce algorithm takes the result from each of those different components and combines it again together into a single result and presents it to the user of that job. So it's MapReduce that does that part. It was popularized by Google. It was Google that popularized MapReduce, and it's used for massive data sets. Really, you will not enjoy Hadoop if you don't have access to big data. Look at a company like MTN. MTN has 75 million active customers. 75 million. So imagine if it is just even 50 million of them that make call in a day. So maybe each of them make 5 calls and receive like 10 calls in a day. Imagine how much data they are going to be generating, plus the data session, internet data session they are generating. So it is only one company that I know today that has been there are 2 companies in Nigeria today that I know that have implemented big data in a very, very big way. That have implemented big data in a very big way. One of them is MTN, and the other one is EcoBank. So EcoBank did a POC where they implemented their their ATM. They decided to implement their ATM on Hadoop infrastructure. If you have EcoBank account, try and go and withdraw money from EcoBank ATM, and then you see the speed. Of course, customers from other banks, if they try to withdraw money, because that is still dependent on the traditional database system. So that one is going to be slow. But if you're an EcoBank customer on EcoBank ATM machine, the speed is when we did that POC then. I really didn't know whether they scaled that project in Nigeria. That we implemented Hadoop. That is the word I want to use. That we implemented Hadoop in Nigeria. But Google popularized it, and they also made it available to the public. And the process would normally start for Hadoop. The process starts with the user submitting a request to the MapReduce program or the MapReduce algorithm, and then that job or that request is split, executed, and the result is combined and returned back to that after it has been executed within a system. It's like a tool that helps businesses to handle structured and unstructured data, which are not easy to analyze with traditional tools. At times, when you're analyzing data, at times it takes a very long time to analyze some type of data set. MapReduce kind of make it very, very easy when you have a big data platform or a Hadoop platform available. It consists of 2 main components. Component number one is map. Component number two is reduce. And that's why they call it map reduce. So map breaks down the job. Reduce combines the job. Don't mind them. So they will just call it any name. You can be confused. You think that reduce should be breaking down the job into smaller components, but it's not so. Reduce is the one that is combining the final result into a single chunk, while map is the one that is breaking down the job into smaller components. So a map reduce worker processes the data from the master and send the result back to the master. And each worker has a unique set of code. Some of those code, they are in the textbook. You see the code that implement map reduce. They can implement map reduce for. I think I implemented it for a project I did with FCMB Bank. So we wanted to analyze all the. So if you look at transaction narrations in the bank, they are unstructured. So if I send money to my mom now, so I'll just say mom. If I pay for DSTV, I write DSTV. Another person does DSTV, write DSTV. Another person can write DSTV in full. So if you look at that particular column, it's unstructured. It's completely unstructured. To a large extent, it's unstructured. So we wanted to know the most frequently occurring words. So those frequently occurring words will make us know what exactly are people spending money on. For a bank like, if you look at a bank like FCMB, they have like quite substantial number of customers. Bank like First Bank has like maybe 10 million active customers. So which is a whole lot, when you analyze all the transactions generated by these people. So now, we now pass that trans narration, for the period, for like a 1 year period, and pass it into a map reduce program. And what it does, I think I still have that project somewhere here. I'm going to be sharing it with you later on, if time allows us, in the course of this class. So what we now did was to, first of all, that is so much of a data set. If you are doing for a full year, it's a whole lot. For 10 million customers for a period of 1 year. So when you take that job, first of all, you need to be able to split it into smaller tasks. And what we are looking for the frequency. We will just want to count the frequency. We want to analyze that and we are looking for frequency of occurrence. We are looking for the frequency of occurrence of some keywords within the narration, so that we'll be able to know what people are spending money on. And whenever we are going to create product, we can create product around that frequency. So take the narrations, pass them into a map reduce job. It will split it into smaller chunks. Then another program will now do the counting. There is going to be a counter that does all the counting. After I count each of the words, then there's now going to be the reduce the reduce that will combine all the results together for each of the words that occur. So maybe in job number 1, blessing occurred 5 times. In job number 2, blessing occurred 3 times. In job number 7, blessing occurred another 7 times, and so on and so forth. Then the reduce will now come, look for blessing, and anywhere you have blessing, it will combine all the blessings together and tell you, okay, the total blessing that we have is 100. Then the total this that we have is 85. The total next one that we have is this, and then it returns the result. So that way it makes it very fast. You now imagine if you want to use your SQL to do that kind of analysis. If you want to use your SQL to do that kind of analysis, to search for the most occurring word, first of all, it's going to be very, very slow. For a full year, I'm not saying for 1 day, for a full year, it's going to be very, very slow, because all you are searching for is string. It's not like numbers that can be indexed. It's string, and there are going to be multiple different options. But really, that is one fantastic use case where MapReduce can be applied in Hadoop file system. And how it works, I just explained how it works. And this diagram is trying to also show how that works. But it's how it works, that is how I just explained it. That's how I just explained it now. So the strength of MapReduce is that they can handle issues better than, they can handle unstructured data better than relational database. Yes, that is the word. They can handle unstructured data better than your relational database. A lot of us here, almost everybody here has interacted with a relational database. But MapReduce can handle some issues a lot better than relational database. And I'll give you an example, especially when it comes to mining text, unstructured kind of data, web log, server logs, data that is scraped from the internet. MapReduce does it a lot better. It MapReduce is at its best when the data when most of the data from a large set of inputs is not required for analysis. So at times we can have a lot of data, but it's not all of them that you need for analysis. It's just some part of it that you need for. It's just some part of it that you need for analysis. MapReduce is very good when it's just some part, or it's not all of the data set that you need for analysis. MapReduce is very good. It's very good when it comes to sorting data. It can sort data for you very well, irrespective of the size of that data. It can sort it very well. MapReduce is also very, very good. If you want to do your ETL, MapReduce can do ETL very well for you in some specific occasions. If you want to do ETL for some kind of data, MapReduce can help you to do it very well. And yeah, so moving on, please feel free to ask me any question if you have it. I wish, so tomorrow I would like us to have a practical session tomorrow. So please, if you have not set up, if you've not set up the virtual platform on your computer, please feel free to come to the office and download that material on your computer and then set it up on your PC so that when we are doing the practical session, it will be easier for you to be able to flow with it. All of these are in the virtual lab that was provided by DASCA. Please ask me your question. Okay, I thought somebody wanted to ask a question. Okay, so what are the downside of MapReduce? So MapReduce is not a database, so it does not have all those security of a database, indexing, query optimizer, all of those things. It does not have it. MapReduce is very fast though. It's very, very fast, but it's not really a database like that. It's not like your Oracle, although you can perform some operations that Oracle will perform. You can use it to analyze your data. You can use it to sort data. You can use it to do a whole lot of things. But you still need to know that it's not a database. So all the features of a database, or all the features of a database, they don't exist in MapReduce. MapReduce is just a mere algorithm that you apply on data. So MapReduce consider every job as an entity in itself. So it's not aware of other processes that may be going on simultaneously. So yeah, it's a downside for MapReduce. So it's not aware. So if you are sorting a data here and you are sorting another data there, MapReduce, you cannot connect two MapReduce jobs together like that. You cannot just easily connect two MapReduce jobs together like that. But remember, in traditional database, when you have a table and you have another table, if one table is on Oracle and another table is on SQL Server, you can find a way of connecting those two data sets together. Data sets that are on different tables can find a way of connecting them together. But MapReduce jobs, they run independent of each other. They are not even aware of their environment. it also comes with the responsibility of the exact type of data that is created in every process. Everything is more or less going to be custom coded. So each time you are working with MapReduce, you need to write a special code. You know, you need to, it requires a lot of customization every time you need to do MapReduce. It requires a whole lot of customization. It's not like, okay, you can just copy and paste what you have done before. No, you need to customize it. So it's a limitation for MapReduce. And even though it's a relatively new concept, maybe over time we are going to overcome some of these limitations. But at least in Hadoop 2, those are some of the downside of MapReduce. So some of those flavors by Hottenwort, AWS, and the rest, some of those flavors, of course, would have found a way to overcome some of these limitations. Okay, so let's pause. Let's pause on this note. It's just about 4 minutes to 7. I think we have consumed a lot for. We've consumed a lot of technical things for today. So maybe we should just pause. I'm sure by the time I'm going to get my feedback this time around, I'm going to get 60% from my evaluator. But nothing spoiled. I'll keep on getting better every now and then. But let's pause at this point. So when we meet tomorrow, if we can, we'll do some practical session. If we cannot, we'll continue talking about the Hadoop ecosystem. Thank you, everyone. Please feel free to ask me any question if you have any question for me. If you don't have any question, see you 2 p.m. tomorrow by the grace of God.
Thank you, blessings.
Thank you, Petra. Okay, everyone, thank you. I don't think I have any question. Bye, everyone. See you 2 p.m. tomorrow. Good night.
Right, good night.
Thank you.